Okay, so what I'm going to show you now is the following. I'm going to show you a molecule here. And I want you guys once again to do this together with me. Okay. So draw this at home. So I'm going to complete the Lewis structure of this molecule. Pretty simple. Okay. So guys, now I'm going to ask you something we also learned before. What is the hybridization on this carbon? I'm sorry, on this oxygen. What's the hybridization of that oxygen? So that is correct. That oxygen is sp2 hybridized because it does have a double bond. Okay. So the second question I'm going to ask as a reminder is the lone pairs of the oxygen in which orbitals are residing. So in which orbitals do we have the lone pairs of this sp2 hybridized oxygen? Anybody remember? No? So I'm gonna once again, and that's why I want to do this before to next class, because I believe this is gonna be a good reminder for you. So guys, an sp2 hybridized atom means that that atom will have 3 sp2 hybrid orbitals, because an sp2 is combining 1s and 2p, so that's 3 total sp2, right? Combining 1s and 2p, 3 sp2, and then in addition to that, there is a pure p orbital. How many sigma bonds do you see in this oxygen? 1 sigma bond. So the first sp2 will have a sigma bond, and the remaining 2 sp2 obviously will be for the lone pair, so that both lone pairs will be in sp2 hybrid orbitals, guys. That's very important to remember. And then the pure p orbital is used for what? For the pi bond. Okay, that's the orbitals around this sp2. Those are the orbitals around this sp2 hybridized oxygen. Okay, now I'm gonna look into this oxygen here. What is the hybridization of that oxygen, guys? That oxygen is also sp2 hybridized because I said in class before that any atom with lone pairs next to an sp2 atom, this is sp2, will also be sp2. So I'm gonna also write this down here. That oxygen is also sp2. Therefore, it has 3 sp2 orbitals and 1 p orbital. How many sigma bonds in this oxygen here, guys? How many sigma bonds? There are 2 sigma bonds. So the first sp2 hybrid orbital will be used for a sigma bond, and the second one as well. So the third sp2 will have a lone pair, and the p orbital will also have a lone pair. Okay, everybody agrees on that. Good. So this is something that is very relevant, because now what I'm going to do is just redraw this. I'm going to just, according to this, I'm going to show you an orbital diagram, very simple. Let's forget about the pi bonds here and the atoms. So I'm basically going to focus on these 3. I'm going to color code this so everybody follows what I'm doing. Okay, I'm focusing on that, on this red area right here. So we agree that there is 2 lone pairs in sp2 hybrid, and there is a p orbital here with with one electron, obviously. So I'm gonna draw that p orbital. In this carbon, which is also sp2, 3 sp2 and 1p, there are 3 sigma bonds. So the 3 sp2 put for the 3 sigma bonds and 1p for the pi bond. So this is a pi bond here, side by side overlapping of p orbitals. And we just agree that this oxygen here, because it's sp2 hybridized, and it has 2 sigma bonds, 2 sp2 hybrid orbitals for the 2 sigma bonds. So one lone pair is in an sp2 hybrid orbital, and the second one is in a pure p orbital. So I'm going to draw my pure p orbital here. My first question here is, how many electrons in p orbitals do we have in this system here? How many electrons in p orbitals total? Okay, how many electrons total, guys, in pure p orbitals? So how many electrons in this p orbital here? This one on the oxygen, on the top oxygen. How many electrons in that p orbital? No, no. How many electrons in this pi bond total, guys? 2 electrons in the pi bond, 1 from this oxygen and 1 from this carbon. Each of these p orbital has just one electron. So 1 here, and how many here in this one? In this p orbital, how many electrons do we have in the last one? 2 electrons, because that p orbital has a lone pair. We just did the orbital picture for each oxygen here. So the total number of electrons is 4 electrons in p orbitals. Okay, now, okay, I'll repeat, Jennifer. So look at the orbital picture here. This oxygen is sp2. 3 sp2 hybrid orbitals and 1p. That's an sp2 atom. Okay, 1 sigma bond for the first sp2. The remaining sp2 hybrid orbitals will be occupied by the lone pairs, and the p orbital is used for the pi bond. Okay, in that p orbital, the oxygen is contributing with 1 electron. Okay, the pi bond is 2 electrons, 1 from each atom. For this oxygen here on the bottom, sp2, 3 sp2 and 1p, 2 sigma bonds. So the remaining sp2 is for 1 lone pair, and the second lone pair, which has 2 electrons, a lone pair in the p orbital. So that's 2 here, 1 and 1. That's a total of 4 electrons. Is that clear now? Everybody, 4 electrons. Very important. Okay. Now, guys, I said many times, I define pi bonds side by side overlapping of pure p orbitals. And we are defining this pi bond. Everybody agrees that this is a pi bond, right? But my question is, don't we have here another 2 p orbitals that are next to another and in the same plane, so properly aligned? So why, if I see a pi bond here, why couldn't be another pi bond over here? In fact, there is pi bond character here too, because same as these two can overlap side by side to form a pi bond, these two can as well, because they have the same symmetry and the same alignment. You guys agree on that? Can you guys see that? So I want everybody to, I'm gonna start pulling questions again, because I don't know if the class is sleeping. Hoping you guys are not, okay? Anyways. So 3 sp2 atoms from next to one another. There have to be interaction here, and there must be interaction here too. The same, it's exactly the same, okay? So when you look at this Lewis structure, I'm gonna put the Lewis structure here, and I have my orbital analysis here. According to my orbital analysis here, I must have pi bond character here and overlapping here too. And according to this Lewis structure, I see a pi bond here, and I can only see a sigma bond here. No indication in this Lewis structure that there is any kind of pi bond over here. Zero indication of that. And in fact, there is. So this single Lewis structure fails to show the real electronic structure of this molecule. So this is a limitation of a Lewis structure, because this Lewis structure is not showing any kind of pi bonds here. So one Lewis structure fails to give you an accurate representation of the electronic structure of the real molecule. So something must be done to resolve this. And that's what we call resonance theory. Guys, resonance theory it's a tool that we use as humans. It's not science, it's a tool that we use to show the real structures of the localized systems. Okay? The localized system. So what is a delocalized system? It's a system in which you have 3 or more sp2 atoms next to each other. Okay, I'm gonna write it over here. The localized system three or more sp2 atoms next to another and properly aligned. So whenever you have, guys, whenever you have 3 sp2 atoms or more next to one another, properly aligned, that's a delocalized system. And in that case, just one Lewis structure is not good enough to show the real structure of that molecule. It fails. So we need to come up with a solution for that problem, and that is resonance theory. And what exactly is the solution? The solution is using, instead of one, we're going to use several Lewis structures to show the real structure of that molecule. And we are going to say that the real structure is a hybrid of all these Lewis structures. Okay? And that's what we're going to learn to do in this chapter, where we will be discussing resonance theory. One of the most important concepts in organic chemistry. That's why I'm going to take the time next class. It's very relevant, not only for this class, but for next semester. But I wanted, at least today, I wanted to show you guys what is the reasoning and what is resonance theory in the first place, and why is that. We use resonance theory when we have delocalized systems. When the systems are localized, when you don't have delocalization, one single Lewis structure is pretty accurate of the real structure of the molecule. So one is enough. No need to use resonance. But when we have a delocalized system, which is a system with 3 or more sp2. I'm going to give you another example quickly before we finish today. Look at this molecule here. Okay, guys, how many p orbitals do we have in that molecule? How many p orbitals total do we have in that molecule? Try again. Everybody's saying 2. How many p orbitals do we have in that molecule? I'm not asking how many pi bonds. We have 4 p orbitals. And they are next to one another. They are right here. So we have 1 here, 2 here, and 4. So we have 4 p orbitals next to another in the same plane. So if we say that there is side-by-side overlapping here and side-by-side overlapping here, what happened with the side-by-side overlapping here? That's missing. That structure is not showing anything that indicates that it is side-by-side overlapping in between these two. So that's a delocalized system. You have 4 consecutive sp2. We need to come up with another structure to show what's going on here, because there is double bond character here too. Okay, that's what resonance theory is about. It's a new language. We're going to learn a new language of how to write molecules, in which we're going to use different curve systems, different kind of writing the structures. That's why resonance is so important. But first is key to understand the science behind this. Why do we need resonance in the first place? And once we understand that, I teach you the language so you can write the resonance language, and then you can express the real structure of these molecules that are delocalized. Okay? So we'll learn that in the next class. So I'm going to stop the recording for now. Thank you guys for being with me today here. Hope you guys are doing